Welcome to When is a Craton Not a Craton? It was Dr. George E. P. Box who drew our attention to the fact that essentially all models are wrong, but some are useful. So, acknowledging right up front that the model we are creating here is wrong, the most important question is, how wrong does it have to be before it is not useful? As the reader, observer of this presentation progresses, she will find that this quote by Dr. Albert Szent-Györgyi summarizes the second half of the presentation perfectly. What are cratons? An excellent summary is presented by Groves and Santosh 2024 in their book titled Mineral Systems, Earth Evolution, and Global Metallogeny. So the summary of what we know is 1. Cratons are subcircular. 2. They are large geological features, often exceeding 1,000 kilometers in diameter. 3. They are a foundation block and represent the older and most stable components of the continental lithosphere. 4. They occupy the central portions of tectonic plates. And 5. They are extremely old, Hadean, 4,000 to 2,500 million years ago. Let's look at the supporting evidence for each of these characteristics of cratons. Let's see the supporting evidence for number 1 and number 2 on our list. The cratons here on Earth. Note that there are many composite cratons. Since cratons are currently subcircular, it is possible through Earth evolution that they were originally circular. West African cratons are very supportive of this speculation. The location of the West African cratons. Major geological features for West Africa. Note that the very oldest rocks, that is the Archean and Paleoproterozoic rocks, are concentrated in the very northern part and the very southern part of this supercraton. The rocks between these ancient, very ancient Archean Paleoproterozoic rocks are much younger, as young as Mesozoic, that is, as young as 66 million years ago. The following movie shows the transition that takes place as we remove the much younger rocks from the Taudini Basin. It becomes obvious that after a 1,000-kilometer migration of the Regwabat Inlier to the south, we have created a complete circular craton. Note that this circular feature is indeed a major geological feature in that it is 1,800 kilometers in diameter. There are many composite cratons on Earth where the two halves merge when younger basinal formations are removed. See the following at our YouTube channel. And number 3 on the list by Groves and Santosh is cratons are a foundation block and represent the older and most stable components of the continental lithosphere. And the reason that cratons are a foundation block is that they have very deep roots.
There are several important takeaways in respect to this cross-section presented by Pierce et al. 2021 in respect to deep continental roots and cratons. The first is the actual extent of cratonized lithosphere, as indicated by the red line, is at different depths. Second, note that the ages of the cratons are correlated directly with the depth of the craton roots. The older the craton, the deeper the root. The importance of these two observations will be developed in the next few slides.
By now the viewer is well aware of points 4 and 5 presented by Groves and Santosh 2024, the most important of which is that cratons are extremely old. In respect to age of cratons, the question that comes to mind is, quote, since cratons are so old, what was happening long ago that is no longer taking place here on Earth? By far the most important event that happened in early Earth evolution was ancient meteor impacts. Following is modeling of the late heavy bombardment, that is 4.5 to 3.5 billion years ago, on the early, that is Hadean and Eoarchean Earth, using the Moon as an analog. The maps are whole Earth mold-wide projections. This model of the early Earth bombardment is the basis of the spatial temporal Earth pattern. The Moon is being used as an analog, always keeping in mind that the gravitational attraction of the Earth is 6 times greater than that of the Moon. Later in this presentation, the gravitational difference between the Moon and the Earth will be discussed in more detail.
It is proposed that each of the major meteor impacts would leave a permanent scar in the mantle. Lesser meteors would disappear through erosion and other processes here on Earth. These permanent scars in the mantle become templates. They become accidental templates, which will be discussed later on in more detail in this presentation. One can see from this model that the largest meteors impacted the Earth in the first few 100 million years. Towards the end of the first billion years, meteors had diminished in size and in number.
This flyover of the moon gives us a good indication of what the Earth looked like 4 billion years ago. And on the Earth, as you can see here on the moon, there would have been multiple meteor impacts for every possible location. As has been mentioned many times, the Earth is an amazingly dynamic planet. However, the Moon, which is essentially a dead planet compared to the Earth, has recorded very early, 4 billion year ago, meteor impacts. So the Moon is a perfect analog for early Earth history.
The fact that the Earth has 6 times the gravitational pull of the Moon means that the Earth will have attracted not only more meteors, but as well much larger meteors, especially billions of years ago.
This simulation illustrates that the largest meteor impacts would have created the deepest roots within cratons. Earlier in this presentation, we mentioned the concept, the idea of an accidental template. What exactly is an accidental template? Ortoliva, 1994, in his book Geochemical Self-Organization, discusses the possibility of many types of internally generated templates existing in self-organized geochemical systems. He also mentions templates that are accidental, those that have been imposed on a system through some external agent. Meteor impact structures may create this type of accidental templating. Deep listric faults, as shown on this artist's rendition of a typical complex meteor impact, would be an important part of that template, giving access to heat well within the mantle. Final comment on the coming together of the two halves of the Western African craton, that after that 1,000-kilometer movement to the south of the Regwabat Inlier, the two halves have joined to create a proposed meteor impact site. The meteor, of course, would have impacted the Earth billions of years ago. Global metallurgy. Gross and Santosh, 2024, present the opinion that meteorite impacts, such as the one acknowledged at Sudbury, were coincidental with the creation of mineral deposits, not causative. However, the paper in 1994 by Grieve and Macetis, titled The Economic Potential of Terrestrial Impact Craters, note that the mineral deposits proximal to known, that is, relatively recent impacts, occur preferentially at the outer rim, that is, the circumference, of the impact, or at its very center. Let us inquire further into the Sudbury, that is the 1,850 million year ago meteor impact in Canada. Note that all of the mineral deposits occur along the circumference of this compressed northwest-southeast direction compression meteor impact. Lightfoot 2017 in his book Nickel Sulfide Ores and Impact Melts, Origin of the Sudbury Igneous Complex, states, quote, "The impact process provided sufficient energy to melt the upper crust as well as produce the pseudotachyllite breccias, syn-impact radial and concentric dikes, and an uneven crater floor covered by an impact melt that crystallized to form the main mass of the Sudbury Igneous Complex." The scale on which ore deposits were formed is a direct function of the thickness of the primary melt sheet and the topography of the crater floor. Dense immiscible magmatic sulfides were localized in physical depressions and cracks in the crater floor where it was possible for sulfides to concentrate. These relationships are examined in ore deposits which formed at the lower contact, in the immediate footwall of contact deposits, and in radial and concentric dikes generated in response to the migration of impact melt into the fractured crust. This reconstruction of the Sudbury impact leaves no doubt that the various mineral deposits are concentric with the peak uplift, which means they are very likely to have formed in the circumference, that is, a listric fault from the meteor impact. There is considerable evidence that the Earth was much hotter in the past, especially in the first few billion years of its existence. The significance of komatiites. Komatiites are rare, ultra-high temperature, that is approximately 1600 degrees Celsius, lavas that were erupted in large quantities up to 3.5 billion years ago, but only very rarely since. They are the signature rock type of a hotter, earlier Earth. Subsequently, the evolution of the early continents controlled the location and extent of major volcanic events, crustal heat flow, and, most important of all, major ore deposit provinces. This table by Groves and Santosh, 2024, shows that the komatiites and ore deposits related to komatiites occur only in the very early Earth. They are represented by the black bars at Raglan and Kambalda Agnew. Komatiite lavas have a unique spinifex texture. This texture is named after a plant called Triodia intermedia, found in Western Australia and Southern Africa. Any geologist who has come in contact with this plant knows that it can penetrate even leather leggings. Very painful. The final conclusions of Groves and Santosh, 2024. Quote, "Despite the increasing emphasis on mineral systems, published economic geology research still involves mainly deposit or smaller scale studies that involve the application of analytical techniques. Such research tends to emphasize complex genetic models at the microscale, that are commonly applied inappropriately to the deposit or district scale and consequently have a minimal application to and impact on global mineral exploration. Groves and Santosh, 2024, do acknowledge, quote, that individual ore deposits are part of larger scale mineral systems that represent anomalous locations in the Earth's crust. They go on to say, quote, as their formation requires conjunctions of critical parameters related to geodynamics, the fertility of underlying crust and mantle lithosphere, crustal architecture, and preservation, it is to be expected that ore deposits evolved in parallel with Earth evolution. However, they fail to realize that the most important part of Earth evolution has been the very early 3,000–4,000 million year ago bombardment of the Earth's surface by meteor impacts. Logical conclusions. What we need to know to find more giant ore deposits. The promotion of thinking and superior concepts. Groves and Santosh, 2024, quote, economic geologists need to improve their exploration performance and discover more ore deposits. This starts at the province selection scale, where exploration involves conceptual targeting before the application of technological methodologies. Some of the critical parameters that should be considered at this conceptual stage in exploration, where expenditure is low, such as geological thought processes preceding high-cost geochemical and geophysical exploration, and ultimate success requires superior concepts. The sentiments presented by Groves and Santosh, 2024, were preceded by this quote from Wood, Hedenquist, 2019, in their article titled Mineral Exploration, Discovering and Defining Ore Deposits. Quote, we propose that improving the way geoscientists think when exploring, being more predictive, is the immediate key to increasing the number of discoveries. Chadha, 2024, has carried out a detailed analysis of the discovery history of 1,332 base metal deposits at two different scales. Conceptual modeling at the project scale is found to be quite modest, constituting less than 10% of the total approach to discovering base metal deposits. While conceptual modeling at the prospect scale, that is a much smaller area covered, is double that at 20%. And as Groves and Santosh and others have said in previous publications, restricting conceptual modeling to prospect and project scaling is very limiting our ability to predict the most likely locations of world-class deposits. What is needed is conceptual modeling at a continental scale. Conceptual models for exploration are needed here. And this scale of modeling, that is continental scale, is the basis for all of the presentations on our YouTube channel. Scaling is important. However, Groves and Santosh, in a paper 2021 titled Craton and Thick Lithosphere Margins, the Sites of Giant Mineral Deposits and Mineral Provinces, have made the following statements. Quote, although most economic geology research is concentrated at the deposit or mineral system scale for single, well-defined deposit groups with a consistent metal association, there are both academic and economic advantages in considering the similar geodynamic setting of deposits having contrasting metal compositions that are traditionally considered unrelated. As an example, there are a range of mineral deposit types or systems that are spatially associated with the margins of long-lived, relatively cold, buoyant Precambrian cratons or lithosphere with thick mantle lithosphere roots. In other words, even though we have categorized mineral deposits in many pigeonholes, the reality is that no matter the type of mineral metal concentration in a deposit, the proximity to a craton is by far the most important criterion. A first example of the quote above from Groves and Santosh 2021 can be seen here in eastern Australia, where giant early Earth ore deposits are located on the circumference of circular magnetic structures. These circular magnetic structures are interpreted to be cratons. One can see that these ancient mineral deposits are approximately all the same age. However, one can see that the metal content of each of these giant ore deposits is quite unique to the deposit. The thing that the deposits have in common is they all occur on the edge of a circular or arcuate structure. And by far the most important thing to acknowledge in respect to creating a craton is that it is an evolutionary process. This process is comprehensively covered by Johnson et al. 2022 in their paper titled Giant Impacts and the Origin and Evolution of Continents. The Pilbara craton is used as an archetype. They show that the oldest preserved continental crust mostly comprises sodic granites of the tonalite trondhjemite granodiorite, that is the TTG series. This series is derived over time through partial melting of hydrated basaltic rocks, that is, amphibolites, at depths of around 25 to 50 kilometers. So the answer to our initial question, that is, when was a craton not a craton, is answered by acknowledging that the major meteor impact on the surface of the Earth billions of years ago eventually evolved into what we now observe as a craton. And the economic significance of this model is tied to the fact that the largest meteor impacts create the deepest penetration through listric faults along the circumference of the meteor impact into the mantle, deeply into the mantle. thereby providing the huge amounts of heat necessary to create giant hydrothermal ore deposits.